Okay. Hello. Okay, you got me again for a while, for about 5 or 6 classes, and the topic is a new book. Well, not a new book. Survival Analysis, 3rd edition. I'm sure you couldn't wait, right? Well, you could wait, but anyhow, that's the new book, and we're starting to talk about the first couple of chapters in this book. That's what we're going to do today, okay? And I actually think that what I'm going to do today, you're going to find pretty easy, because a lot of what we're going to do about survival analysis is going to be very similar to what we did with logistic regression analysis. A lot of similar things. When we talk about the model for, we're not going to get to the model today, but when we talk about the model that's used for the most popular model for carrying out a survival analysis, anybody know what that's called? I didn't hear. Called the Cox Proportional Hazards Model. And when we talk about that model, which we'll do not this week, beginning of next week, maybe the end of this week, we're going to see that that model, although it has a different form than the logistic model, you work with it almost the same way. In fact, we'll even see a little bit about that today before the end of the class. So there's some differences, but there are a lot of similarities between survival analysis and logistic regression analysis. Particularly, remember all semester up to this point when we were computing, doing logistic regression, we were getting until the last lecture when we were talking about what the measure of effect that we were going to look at for logistic regression, what was the measure of effect called? What was it? Logistic regression was an odds ratio, right? And we looked at a formula for getting the odds ratio. Okay. Now, it's true in the last class, Eli talked about how you might estimate the risk ratio or the prevalence ratio. Turns out that when you're doing survival analysis and you're using, well, whether you're using modeling or not, the measure of effect is not an odds ratio or a risk ratio. It's called a hazard ratio. Okay. But it has the same kind of interpretation as an odds ratio or a risk ratio. If you remember when if the odds ratio or the risk ratio was equal to 1, what did that mean? No effect, right? If the odds ratio was 4, that meant that the effect in one group, say the exposure was 4 times the effect in the other group. Same thing for a hazard ratio. If the hazard ratio is 1, no effect. Hazard ratio is 4, that means a strong effect from one group to the other, or if it's 1/4. So we'll see that. But we're going to start talking about it in very simple terms here by looking at this screen here with a bunch of data. So that's how we're going to start, okay? Talking about survival analysis. And what this data basically says, it's data on leukemia patients who are in remission. And the data gives the time that they were in remission over a certain number of weeks that were in remission until they went out of remission. So what you may see from this, what's shown here, is that there are 2 groups. There's one group getting a treatment, main new treatment of interest, and there's another group too that's getting the sort of the standard treatment, which in this case is being referred to as the placebo. And there's 21 people in each group, okay? And in each group, as you can see, there are numbers here, which is the time for each person in each of the groups that they were in remission until they went out of remission. So the 6 says what? The 6 says this person was in remission for 6 weeks, and after 6 weeks they went out of remission. So you start worrying about their leukemia coming back, and so on. And so that's the way it is for group 1, and group 2, there's some more numbers. There's 21 numbers in each group. But you notice that there are some numbers here that have a plus next to it, okay? 6 plus, 9 plus, 10 plus, okay? That's true in this group, but none of these people have a plus next to it. So the plus means, like the 6 plus says that this person was in remission for 6 weeks, but after 6 weeks, we don't know what happened to them. We really don't know whether they went out of remission at 6 weeks. All we know is they were in remission through 6 weeks, but after that, we don't know what happened to them. And when that happens, we call that kind of data censored data, because the true results on them, we don't really know. So it's censored data. That's the term that's used. So as you can see that in the group that got the treatment, some people weren't censored. They failed. They went out of remission, and a whole bunch of them were censored. But in the group that got the placebo, everyone eventually failed. That's a term that everyone in the group 2 went out of remission. Now, what's this here? Quit? I'll quit. We're not quitting, but okay. So now, if you just look at this data and you didn't know anything about survival analysis, and some of you have already had something about survival analysis in other classes, is that right? Something? What other classes? 530. You had it a little bit in 530. Okay. I don't think you actually had the Cox proportional hazards model in 530, but you had a little bit about maybe what a hazard function or what you meant by survival analysis, and maybe you even had something called the Kaplan-Meier curve. Yeah, okay. We'll talk about Kaplan-Meier curve on Thursday, okay? But anyhow, you look at this data, and I mean, what's the question of interest? The main question of interest is the people who are getting the treatment, are they surviving longer? Are they staying in remission longer than the people who are getting the placebo? If they were, then the treatment's doing better. Well, you hope it might be statistically better, and you might want to measure something, how better they're doing, but that's the main question. Are the people getting the treatment doing better than the people who are getting the placebo? And by getting better, you mean their remission times are longer, because the longer they're in remission, the longer they're sort of surviving, or the longer they're okay. And once they go out of remission, then they're not okay anymore. So if you looked at these numbers and you wanted to draw a conclusion, you didn't know anything about hardly anything, you didn't know anything about survival analysis, what would you say? Which one's doing better? Well, you'd probably say the treatment group is doing better, because more or less the numbers in the treatment group are larger. Collectively speaking, they're larger. Okay? In fact, if you start looking at the numbers like any one of these things with the plus, like the 17 plus or the 32 plus, the 32 plus means they were in remission for at least 32 weeks. You don't know when they went out of remission, but it was at least 32 weeks, so maybe it was 35 weeks, maybe it was 40 weeks. You don't know how long they were there. But so the amount of time the people with the pluses were in remission was even longer than you see. So these numbers, in some collective sense, are larger than the numbers here. So, without even doing anything fancy, you'd probably say, well, okay, I don't really care about doing survival. The treatment group's doing better. Okay, so then how do you pin that down a little bit better? Well, one thing you could do is you say, well, look, I got a bunch of numbers over here on the left for the treatment. Well, I'll get an average of these numbers. So I'll add up the numbers, divide by 21, since there are 21 numbers, and I'll get an average survival time, average remission time. And if I do that, if I add up these numbers and divide by 21, I get 17.1. Okay, that's the average remission time using these numbers. Okay, and if I do the same for the placebo group, I get 8.6. Right? I mean, that's what I get. You could do it, but that's what I get. Okay, so as it turns out that if I use these averages, it certainly looks like doing some kind of summary statistic, which is what we often do when we have numbers. It looks like we got, again, evidence that the treatment group is doing better and doing something a little bit more than just looking collectively at the numbers. Okay. Now, you got to realize, though, that the 17.1 isn't the true average for the treatment group. Why is that? What's the true average remission time for the treatment group? Well, we don't know what it is, but is it higher or lower? It's higher than 17.1 because anybody with a plus, their remission time was longer, even though we don't know what it is, right? So, this isn't exactly right for the mean for the treatment group, but certainly it's even bigger. There's even a bigger difference, okay? Now, one thing you might be tempted to do if you saw these two numbers and just sort of ignored the fact that there were pluses there, you might say, well, look, I got two means. I got two average values, two sample means. What do you usually do when you have two sample means? You learned this in your biostatistics course last year. You do like a two-sample t-test comparing two means, right? So you could do that. You might consider doing that. But there's a problem doing that. The problem actually doing that is the fact that this 17.1 isn't the real mean. So if you do it, you're not exactly doing something that's exactly right. Okay? Even though you could do that as sort of something, as an approximation to something, and people sometimes do that. But there's something you can do that's better. Something that you can do that's better, and that's to say, well, the mean isn't really necessarily the best thing I want to measure for this. What I actually want to measure is something called a rate. And you've heard about rates because you learned about that last year a little bit, and you're going to learn more about that now and later on in the course when we talk about another model called Poisson regression model. But what we mean by a rate, you may remember, what's a rate? A rate has to do with when the outcome is a count, and in this case, the count that we're worried about is the number of people in each group, or just focusing on a given group, the number of people in a given group that went out of remission or that failed. So how many people in group 1 failed? I'm talking about went out of remission. You can count them because the number of people that failed were the ones that don't have pluses on them. Because the ones with pluses, you don't know what happened to them. Maybe they failed or they went out of remission, but you don't know when. So you count this as 9. Okay, there were 9 people that failed. 9 people went out of remission. How many went out of remission in group 2? All 21. Okay. So what do you do to get a rate? What's a rate? You get a count, number of events that occurred, and you divide it by, what do you divide it by? You divide it by a proportion, the number of people at risk? No, you divide it by something called person time. The amount of time contributed to all this information of follow-up contributed by all the people together. How do you get the person time information for group 2? How do you get that? You just add up all these numbers. This person contributed 1 week, another week, 2 weeks, 2 weeks. Add up all the numbers. You get the person time for group 2. How do you get the person time for group 1? Well, you add up all these numbers. I mean, this person was 6 plus, but we know that person contributed 6. We don't know what it contributed afterwards, but we know it was at least 6, so that's the information we have on. So if we add up all the numbers for group 1, we get the person time for group 1. We add up all the numbers for group 2, we get the person time for group 2. So how do we get a rate? What's a rate? Well, it's the number of failures divided by the person time, which is the sum of the times for each group. So that's what you get. You get a rate. So this would be 9 divided by the sum, and this would be 21 divided by this sum. Okay? And if you actually carry that out, do the algebra, the arithmetic, you wind up, and there it is, 9 out of 20, 9 out of 21, the 21 in each group, but the 21 isn't the person time. That's, the person time is the sum of this. So I don't have the person time for each group in here, but if I actually do it, what I wind up getting is 9 over the sum of this turns out to be 0.025. And 21 over the sum of these turns out to be 1.115. So the rate for group 1 is 0.025, and the rate for group 2 is 0.115. That's what the rates are. The rate is the number of events, or the count, the number of times the event occurred during the time of the study over the person time separately for each group. And this is actually, it's a rate, but it's actually, there's a name that's usually given to it. It's called the hazard rate. And it's actually, there is something that we're going to talk about shortly called the instantaneous rate. So this is actually something called the average hazard rate. And the reason why I've got an H over here is H stands for hazard. And the reason why I got a bar over it is because it's an average. It's an average. Okay. So now what you notice is, well, what you can see from this, what's on this slide is that, and I haven't talked anything theoretically about what's survival now, but what you see from this data is that you notice that the mean, or ignoring the pluses, for group 1 was higher than the mean for group 2. But what do you notice about the rates for group 1? It's smaller than the rate for group 2. And does that make sense? Well, if you think about it, it makes sense, because when you're talking about the means, we're focusing on surviving, how long they last. When we're talking about the rate, we're talking about failing, how long they don't last. You know, how long they go out of remission, or how many people go out of remission. So we would expect that if this average is higher than this one, this average rate would be smaller than this one, and sure enough it is. Okay. So we now have, and this hazard rate for each group is a legitimate thing. There's no approximations here. It's a legitimate descriptive statistic that you could make for each of these two groups. You're not approximating it. You're doing the denominator is the number of person weeks. Okay. So one group, again, group 1 is doing better than group 2 because its average hazard, and the hazard, again, the word hazard means danger, you know. So hazard has to do with not doing well. So the higher the hazard, the worse somebody's doing. The lower the hazard, the better. Okay, so group 1 is doing better because its average hazard is lower than the average hazard for group 2. That's survival analysis. Now, one thing typically we do, like we do if we had a 2x2 table, if we had two things we wanted to compare, and we want to compare group 1 with group 2, and we have these two hazards, one for group 1, one for group 2. Well, we'd say, let's take one hazard and either subtract it or divide it by the other hazard. And if we subtract it, we get something called a risk difference if we're dealing with like a 2x2 table. But if we're doing the survival analysis, we're not getting a risk difference, we're getting a hazard difference. And if we take a ratio, we're getting what's called a hazard ratio. And that's the main measure of effect. So the hazard ratio would be one of these hazards over the other. Okay? Now, I could take the hazard ratio of 0.025 and divide it by 0.115, and if I do that, I'll get a number less than 1, okay? And I could have done that. I could say the hazard ratio comparing group 1 to group 2 is some number less than 1. If I do it the other way around, if I compare group 2 in the numerator over group 1, I get a hazard ratio of 4.6, okay? It doesn't matter which way I do it, but what people often want to do is get ratio estimates that are larger than 1 because they're easy to interpret. If you see the hazard ratio is 4.6, you can say, well, the hazard for one group is 4.6 times the hazard for the other group. So it's easier to interpret than if the hazard was 0.382. I don't know what the ratio would be, but it's easier to interpret. So that's why typically when you have two or more groups you're comparing, you usually get the hazard ratio to be some number larger than 1, even though you still can interpret if it's less than 1. Okay. So in this case, you've got some information that it looks like the treatment is effective, that collectively it looks like it's effective, and if we look at the information and get some descriptive statistic, the better descriptive statistic here is the average hazard, and we get a hazard ratio of 4.6. So it looks like we got something here, or there's something that shows that the treatment's effective. Is that enough? Is that enough? Well, why isn't it necessarily enough? You remember when we talked, and this is just the crude data. In other words, one reason why it's not enough is because I'm not controlling for anything else, right? This is what we typically have done with logistic regression. We have two groups we want to compare. We want to control for other variables, confounders, effect modifiers. Haven't mentioned that at this point. So that makes it complicated. But suppose we just focus on these two groups, and we don't worry about other variables at this point we want to control for. What have we done and what haven't we done with this? Well, we got a point estimate of the effect. We got a hazard ratio of 4.6. What don't we have? We don't have anything, and we can get it, but we don't have it right now, whether it's statistically significant, right? So that's another thing we want to do. We want to get the point estimate, and we want to decide whether it's statistically significant from 1, the null value of 1. That's the hazard ratio, null value. We don't have that here. We'll learn about how to do that, okay? And what else do we want to get? Point estimate, test of hypothesis. What's the third thing we want to get? Confidence interval. We don't have that either, but we'd want to get a confidence interval because what does that do? Tells us something about, you know the words, you've been having it all semester here, and precision. The confidence interval gives you something about precision. So ideally, when you're doing a survival analysis, whether you're doing a simple one or a more complicated one, you want to get 3 things. And this is true whether you're doing logistic regression or something or anything else. Anything more complicated, like if you go on to the next semester, you do longitudinal correlated data, you want to get 3 things out of your analysis, no matter how simple or how complex it is. You want to get a point estimate of what you're trying to evaluate, an interval estimate, and a test of hypothesis. And we only right now have the point estimate, right? So we're going to move on to these other things. Okay? So that's sort of what a survival analysis is doing, at least in this example. I think you got that, right? Okay, so let's talk about what is a survival analysis. We'll talk about some of the features and go into that. And this is really the first chapter in the book. So what is survival analysis? What do we mean by censored data? What's some of the terms, the notation that we're going to use? What are the goals of survival? Now, what does the data layout look like? And some examples, and a little example about mathematical modeling. So that's what we're going to do today, okay? And there's a lot of people who've written a lot of things about survival analysis. I've listed a whole bunch of things, and there's one over here that's in red. Why is that in red? Because that's this thing, right? Okay. This is the one of all these things, not necessarily all, but this is the one that I like to say, I may have said this about the logistic regression book, is I like to say it reads like a novel. Ha, 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 right? Or a mystery novel, I don't know. But people keep telling me about this and that it reads nicely. Because, this was written, I don't know, I may have mentioned this before about the logistic. These books are written sort of like, they're like PowerPoint presentations. In fact, they were written, this was before there was PowerPoint. These were written before there was PowerPoint. There's a page with the lecture, and then there's a page with the formulas. So this is PowerPoint before PowerPoint. Okay. Whoa, it was my idea, I didn't invent PowerPoint. Who was the guy who invented the internet? Al Gore, right? I don't know. So anyhow, so let's talk about survival analysis. So what is survival analysis? Okay, it's as I say here, it's a bunch of statistical things, procedures for doing data analysis for a certain situation, certain data situation, and the data situation is such that the outcome variable is different from the outcome variable we've been talking about up to this point, where the outcome variable was either binary or it could have had 3 or more categories. Now the outcome variable is a continuous variable, and it's a variable that involves time. And it's time until something happens, and the something is often called an event. The event could be a good thing, somebody's cured, or it could be something bad, they go out of remission, or they die. So it's time until something occurs. time until an event occurs, okay? And that's the outcome variable. That's what you're trying to predict, or that's what you're trying to describe. You're trying to see whether an exposure variable helps to explain what happens, how long it takes for somebody to get an event, and comparing groups and so on. And when you're talking about time until an event occurs, the study you're talking about is a follow-up study. It's typically a prospective study that's going forward in time, or certainly a follow-up study, starting with people that don't have the outcome and you're following them to see if they get the outcome. So it's a follow-up study, time until you get the event. Okay. Now, as I was saying, the event could be any one of a number of things. It could be death, whether somebody died, follow up until somebody died. Could be time until somebody gets a disease, time until they actually get a cancer or something like that, time until they get a heart attack, time until they get something else. It could be time until they relapse from something. Relapse like in remission. They're in remission and then they relapse. They go out of remission. Or it could be time until they get better, time until they recover. So it could be any one of these things, okay? And it depends on what you're dealing with. So, but typically we often call it a failure, even if the event that we're dealing with is a good thing. We often say time until the event. If the event happens, even if it's good, we say they failed. They got the event, even though it really might be a success, okay? Now, another thing to say about this is what I have in this little box over here, is that we're going to assume throughout the rest of this course, when we talk about survival analysis, that we're only interested in a single event. There's only one thing that we're worried about getting. We're only worried about whether they die. We're only worried about whether they get a certain cancer. We're not worried about whether they get this event or that event any more than one event. We're only focusing on one event. And if we were worried about whether they could get this event or any one of three events that they might get, depending upon what happens to them over the time, that's called, those events are called competing events. And that kind of analysis is called a competing risk analysis. Now, there is a chapter in this book about competing risks, but we're not going to get to that because that's just too much. Too much to do. So, but it deals with how you deal with more, where the number of events is more than one. Now, time. What about the variable time? The time until an event. What are the units of time? Well, they could be whatever units you think make sense, given what you're studying and how long it takes, given the illness you're studying, or given how long you're following people. Could be years, weeks, days, whatever it is, or it could even be the age at the event. I mean, that's a time thing. How old were they when they died? Were they 60? Were they 65? How old were they? That's a time variable, right? So it even could be age at the event. Okay, so that's there's and when we talk about the time, we often we actually interchangeably often sometimes say survival time because that's how long they lasted, so they survived that long. But you could say failure time. There's time until they failed. They survived this long, after which they failed. There's just two ways. You have to decide what you want to use. Most people say survival time, and when they talk about the event occurring, they say it failed. But it's different strokes for different folks. I don't know, whatever. But now, a key problem, as we already saw from the example, is that you might not know the survival time exactly for everybody. You might, but in many situations, you don't know the survival time. You follow people for a certain amount of time, and they leave the study. They leave the community. You don't know what happened to them. They dropped out of the study. So you follow them up to a point, and it looks like they hadn't died yet, if that's the outcome, and then you lost them. You don't know whether they died or whether they're still alive or whatever. So that's censored data. And when that happens, what do you do? How do you deal with censored data when you're trying to do the analysis? We already saw one way to do that is to deal with it by using not an average value, a mean, but using a rate to deal with how long they're in the study and the person time information. So that's one way of dealing with it. But that's a problem. That's a key problem. So, okay. So now, different kinds of situations for survival analysis. We've already looked at the leukemia patients. So that's one situation. The outcome is time in remission in weeks. And the outcome is when they went out of remission, when they failed by going out of remission. They relapsed from being in good shape, reasonable shape. Another thing could be you starting out, I mean, in this case, people are already diseased, and you are seeing how already diseased, but they were in remission. Now, it could be you're dealing with people who don't have a disease at all. They're disease-free, and you just want to know time until they develop heart disease, or time until they get a heart attack, or time until they have high cholesterol, or whatever you want to talk about. So that's a different thing. Could be the disease-free cohort. You could have an elderly population. Ooh, 60 plus, is that elderly? Well, I got to be careful there, because some people around here are way past that. Okay, so but if you're dealing with a so-called elderly population, it could be your outcome's death, time until they die. You could be interested in death even if it's not an elderly population. Then there's another thing that there's a lot of literature in the sociology field about people, and this is obviously a big topic nowadays with all the things that happen in the news over the last several months. People get arrested, they get put into jail for a while, and then they go on parole. They get out on parole if they are allowed to do that, okay? And then what often happens when people go out on parole, they either do well or they do something to get rearrested again. And if they got rearrested, that's called, what's that called? Recidivism. Okay. So there are these studies called recidivism studies. Okay. And so in that case, the question is, you may have, the data may be people who, a subset of people, or it could be two groups of people that were put on parole, and then what you want to know is how long they stayed on parole without getting rearrested, okay? Time until rearrest, time until they, I don't know whether this is a legitimate word, time until they recidivated. Is that legitimate? Not sure, just made that up, or maybe there is a word. Time until they rearrest. So that's another example. And then, of course, another example that we're going to talk about later, a couple of weeks from now, is heart transplants. Time until death. You got people who have a serious heart problem, and they become eligible to get put on a list for people to get a heart transplant, and they have to remember how if you don't know necessarily, but if you're in that situation, you often have to wait until a transplant comes along that matches you in some way, and then the question still is, if you get a transplant, how long do you survive with that transplant, versus if you never got a transplant, how long do you survive? That's still a survival analysis question. Okay, so these are all examples. Okay, now let's talk a little bit about censoring. Again, censoring generally means we don't know the survival time exactly, and there's different kinds of censoring. And what we usually deal with, even though there are other kinds, and what we're going to deal with in this course, because there's enough to say about this kind of thing without getting into other kinds of censoring, but we usually deal with something called right censoring. Right censoring. And this is something you probably had in 530, maybe. So, and what you mean by right censoring is that a person's survival time is at least as large as the time information observed. So in the leukemia example, it may be that you got somebody that was in there at the start of the study, okay, and the study ended. I mean, that's one way this can happen. The study ended, and they still were in remission. We're talking about how long were they in remission, okay? And if that's the case, their remission time is the whole time that they were in the study, from the time they got in until the end of the study. But if you're talking about time until they went out of remission, you don't know that. All you know is they were in remission the whole amount of time of the study. The time at which they went out of remission has got to be, if they go out of remission, has got to be larger than that. So this is an example where a person's survival time is at least as large as the time information observed. If somebody survived the whole study, then they're right-censored. You don't know their true survival time, but it was at least as large as what you observed. Okay? And that could happen, if they survived the whole study, or it could happen if the study event ends in no event. That's what I just said. It could happen if they're lost to follow-up before the study ends. Okay? If they're lost to follow-up before the study ends, then their true survival time is longer than what you've observed. If they withdrew from the study before the study ends, their survival time is longer than what you observed. So that's right censoring. Okay? And that's what typically happens, but it's not the only kind of censoring. And the other kind of censoring, there's actually even something called interval censoring, where you're not even sure whether it's between, but there's the other kind that's usually contrasted with right censoring, which we're not going to get into in any big way here, but the going to mention is something called left censoring. Left censoring occurs when a person's true survival time is less than or equal to the information observed. I haven't given you an example on it, but this is an example of that when you're dealing with HIV. Okay. Now, when you're talking about, if you're asking the question of, you're saying, what's their survival time up until somebody got HIV, exposed to HIV? Okay. Think about this. Okay. Survival time until somebody got exposed. Now, how do you detect whether somebody actually has HIV? What do you do? They have to have a test, right? They have to have a test. And if they have a test, and the test says they're positive, that means they already have HIV. Well, when did they get it? They got it before the test was done, right? So their true survival time up to the time they got HIV is actually less than the time you've observed when you found out that they were positive. That's left censoring. That's an example of left censoring. The true survival time up until the time they were exposed is less than the amount of observed time. That's an example of left censoring. And again, this is another issue that one deals with, and one could do analysis on this. In fact, about 10 years ago, one of my master's students wanted to do a master's thesis about how do you analyze left censored data. So she did. And there's literature on that, but we're not going to do much other than to say that's what it is. Okay. So now let's look at this example. Going on here. Let's look at this example. Simple example. Here's a study with 6 subjects. Okay. First subject A, and it's a study that's 12 weeks. Okay. First study A is followed for 5 weeks, and X means they got the event. If you see an X, that means they failed. Okay. So their survival time is 5. Okay. Person B was followed for the entire study, 12 weeks, and they didn't get the event. So this person, first person A, is not censored. They failed, and the second person didn't fail, so they were censored. So if you don't fail, you're censored. That's one of the characteristics of a survival study. Okay. Now, what about person C? Well, they didn't enter at the beginning of the study. They entered, I guess it looks like about 3 weeks. And they were followed for another 3.5 weeks, and then they pulled out of the study. They withdrew from the study. So is this person censored, or did they fail? Well, they're censored because you don't see an X, right? Big deal. Okay, what's their survival time? Well, I put down 3.5. Why didn't I put down 6.5? Because they didn't enter the study until time 3. So you don't start counting them until they enter. Okay. So, and this person was censored, and this person was also censored They entered at 4 weeks, and they were followed for 8 weeks. The study ended, and they still were whatever it was. They didn't get the event. They were in remission or whatever it was. So this is also censored at 8 weeks. And this person came in, again, at 3 weeks, followed for 6 weeks. They were lost, also censored. This person came in at 8 weeks, was followed for 3.5 weeks, and failed. Okay. Now you notice this person and this person have the same survival time. Okay. Even though they didn't enter at the same time. So one thing you got to recognize is when you're talking about survival time, you're talking about the time from when they entered until the time that they either were censored or failed. Now, if this person had actually failed after 3.5 weeks, so we would have, and if this person therefore had an X over here, we wouldn't be considering this person any different from this person. The difference now is this one was censored and this one failed. But if this person had an X over here, as far as we're concerned, they're treated the same way. They were followed for 3.5 weeks and they both failed, even though they came in at different times. That's how when you do the analysis, that's one way you have to do it. So now when you have data like this, it's only 6 people, what you typically do is you get that information and you put it into a data layout. Okay? So in this case, the data layout, you'd have one column which has the ID of all the people in your study, persons A, B, C, D, E, F, and then you'd have, well, there's 2 bits of information we have here on these people. We have 2 things. We have their survival time, 5, 12, 3.5, and so on. We need to know that, but that's not enough. We're talking about survival. We also need to know whether they were failed or whether they were censored. So we actually have another column over here that we have to put in. So when we're talking about survival analysis, the data, what happens to people, there's 2 parts of the outcomes. The survival time and whether or not they failed. They both have to be considered when you're trying to figure out what's going on. Okay. Now let me ask you this. Suppose it turns out that some of these 6 people, or 3 of the 6 people were exposed and the other 3 were unexposed, whatever exposure was. How would you represent that in this data layout? What would you have to do? What would you have to do if you wanted to also add to your data layout something that distinguished exposed from unexposed? What would you do? You'd add another column, right? And that column would be exposure status, a 1 or a 0, right? And if you had a variable that represented a confounder, whether they smoked or what their age was, you'd add another column, right? So that's how you build up a data set. But you have to have, when you're doing a survival, you have to have these 2 columns to consider the outcome. And then you add whatever other columns you want to do to consider any other variables that you're interested in looking at to evaluate the relationship of interest. Okay, so that's the data. Okay, now, some terminology. Okay, I'm going through all this stuff. This is all very important, basic stuff. Okay. First thing is we have to have some term to call survival time. So since it's time, we're going to use capital T for survival time. And this represents, as I said, it's a random variable. What's a random variable? A random variable is from one person to the next. It's a number that can vary from one person to the next. It has variation. It could randomly vary from one person to another. So we're going to call the survival time for a person, we're going to denote that by capital T. And then if we're interested I'll give you an example in a second. If we're interested in a specific time, we're going to denote that with a little t, a specific value of t. Now, one reason why I say that, you see the 5 years, survive greater than 5 years. Where does that come in practice? Where have you ever seen 5-year survival? Well, anybody that's done any look at or read anything about cancer patients, if you've had cancer and you've been treated for cancer and you've gotten over the treatment and you're better for more than 5 years, that's great. You've got 5-year survival. Okay. So you might ask the question, what's the probability that somebody, since they've been treated for cancer, somebody's probability for failure for getting the cancer again, is greater than 5 years, follow-up. Then you're talking about a little t of 5. So if you're talking about what's the probability that somebody's survival time is greater than a specific value of interest, the specific value might be 5, it might be 10, depending on what you're dealing with. But that's what the little t stands for. Okay. So one of the key, in any case, one of the key variables in terms of this picture is survival time, and I'm calling that capital T. Another key variable is whether or not they failed or were censored. So we're going to give a name to that, and we're going to call that variable D. It's a 0-1 variable. It's 1 if you failed and 0 if you were censored. If you didn't fail, you were censored. I mean, if you didn't fail during the time of the study, you don't know what happened to them, you were censored. There's no other thing. It's not that they didn't, it's true they didn't fail, but you don't know what their true survival time is. So we're going to call that variable D. So these are three important things. The capital T and the D are the two key things here. Two key things that correspond to what's here in these two columns. This is the capital T and this is the D value. Okay. Okay, now there's two other terms that are very important when you're doing a survival analysis. One is called the survivor function or the survivor probability. Okay, very important that you want to get out of a survival analysis. And it's defined to be the survival probability at time t, little time t. What's the probability that somebody's survival time is greater than some specified value? Okay, now let me ask you something about this. It's called the survivor function. At time 0, at time t equal to 0, what's the probability that somebody is going to survive longer than when the study starts or when they entered the study? 1. Probability at the start is always S of t, S of 0. When t is equal to 0, S of t or S of 0 is 1. Okay. What happens after that? Goes down, right? Does it go down the same way for everybody? Not necessarily. In fact, it might not go down the same way if you're exposed than if you're unexposed. And so when you're talking about how it goes down from time 0 on, we're talking about a survival curve that might be different for different groups. One group, one exposed, one unexposed. It might be different. So that's the survival. That's something very important. You want to get that when you're doing a survival analysis. Okay. Then there's another thing that's related to the survival function that we also have to talk about. It's called the hazard function. This is a little bit more difficult, but you've heard the term, or you've already heard the term already because I talked about the hazard rate or the average hazard and the hazard ratio. So there's something called the hazard function. It's also sometimes called the conditional failure rate. And it's a rate, and it has to do a rate for failing. So when you're talking about a hazard function, you're talking about a hazard having to do with failing. When you're talking about survivor function, we're talking about surviving. They're on the opposite ends of the coin, some say. So here's the definition of a hazard function. Now, I need to spend a little more time talking about this. Now, here's the definition. Now, if you look at this definition, it's a little complicated because one of the first things you see over here is the limit. And that gets people nervous, right? Get you nervous? What do you remember? Anybody remember anything when you were a kid or in high school or in college when you ever saw limits? What did that have to do with anything? Calculus. How many of you have had calculus? That's when you had calculus, there were limits in there. So that's where you might have first seen it. Could be other places. Okay, so that's part of the thing. This makes it hard. Now another thing you notice is something over here, and it's got this vertical line. What's the vertical line mean? Given. Okay, and when it says given, that means another way of saying given is conditional. In other words, what's the probability that this happens given this? See that? What's the probability of what's over here to the left of the vertical line, given that what happens on the right of the vertical? So what does this say? What is it? Now we won't look at the denominator yet, but look, what does this say? What's the probability that somebody's survival time, person's survival time, is between time t, specific time t, and time t plus a little bit further than time t, a little bit after time t? What's the probability that somebody failed in this interval between time t and t plus delta t? That's what that says. And what does the thing on the right say? What's the probability that somebody fails within a short time interval, t to t plus delta t, given that they survived up to time t? That's what it says. What's the probability that they fail in a short time interval once they got up to the point where they were okay at time t? They survived up to time t. Now, this numerator is a probability statement, right? The numerator. So it's got to be a number between 0 and 1, right? But a hazard function, which is a rate, is not a function between 0 and 1. A hazard rate, the lowest the hazard rate could be is 0. And a hazard rate has necessarily no upper bound. What makes this not a probability? Well, what's in the denominator? You're taking this probability and divided by delta t, the small time interval you're talking about. So this is like, what's the probability that somebody fails in a small unit of time, given they survive up to that time, per unit time? Once you're saying per unit time, you're talking about person time. And then you're dealing with a rate. That's what you're doing. Okay. So so that's what this part of the thing before you even take the limit. Okay. Now what's the limit doing? The limits, this is start getting, what the limit's doing, it's saying, well, we're talking about a small unit of time from a time t. And what we're doing is we're saying, what if we get closer and closer to time t? What's the probability that somebody fails in a small time unit beyond time t per unit time as that unit gets smaller, as we get closer and closer to t? Okay. Well, what we're talking about is a sort of a failure rate at time t, or sort of what's often referred to as an instantaneous failure rate. It's like what happens at time t. What's the likelihood that somebody's going to fail instantly at time t? Okay. Now, we generally can't measure that when we do survival analysis. But, we can measure that when we're driving a car. If we're driving a car and we look at the speedometer, at any point, and we're in the U.S., so we're looking at, what are we looking at, miles per hour. If the speedometer says 65 miles an hour, what does that say? Does that tell you that in the next hour you're going to cover 65 miles? It's telling you at that point, at that moment, when you looked at your speedometer, that's how fast you're going. That's how many miles you would have traveled if nothing changes for the next hour. That's an instantaneous rate. And that's what this is. A hazard function is an instantaneous potential for failing. That's what it is. Now, there are a couple of things, so I'll say a couple more things about this, but in any case, turns out that this is a little bit more complicated than this one, but it turns out mathematically, if you know one, you can get the other. So it turns out that when we do survival analyses, and a lot of survival models are stated as hazard function models, turns out you can go from the way it's stated to getting a survival probability. So even though they look like they're two different things, they're related to one another. You can go from one to another. You had a question, Jake? No? Okay. And in fact, this is the relationship. Well, this is not the relationship. This is later. But so what I've basically said up to this point, I've said a bunch of different things. One thing I said, a survival function is a function that starts at 1 and goes down towards 0, right? It's always 1 at 0 and it's going down to 0. Now, how it goes down to 0, whether it goes down this way or it goes down faster to 0, depends upon what you're studying. But that's what a survival function theoretically looks like. When you actually have data and you want to plot a survival function from data, it's usually plotted as a step function, not as a smooth function. Usually plotted as a step function because you don't necessarily have a continuous number of, when you're following people, you don't have a continuous bunch of time points at which you're asking them how far, whether they've survived or not. And so you don't have a continuous thing to draw a continuous curve. So the best you usually can do is a step function. So when we start seeing actual survivor functions, when we're talking about data analysis, they're going to look like this. Okay. Now, there's more things. Okay. So I just talked about the hazard function. Okay. How are we doing, by the way? Is this horrible? We following this? We haven't done anything that fancy, but the hazard function. Okay, so, and there it is. There's that speedometer. Okay, so it's one synonym is instantaneous conditional failure rate. Another one is instantaneous incidence density. Another one is force of morbidity or mortality. It's an instantaneous potential for failing at time t. That's what it is. Okay. The key property, it's a rate, so it's got to be at least 0, but there's no upper bound. And as I said, it's the instantaneous potential for failure per unit time given survival up to t. Now, typically, we never can get the actual instantaneous. We usually get average rates, just like I showed you when I did the original data set with the remission times. So you usually get average hazards. Okay. Now, remember I said if you know the survival, you can get the hazard, and vice versa. So I want to say something about that. Okay. Now, there's a mathematical formula which tells you how you can get the survivor curve from the hazard ratio, or how you can get the hazard so from the hazard function, how you can get the hazard function for the survivor curve. You see this formula? What's in this formula that relates to calculus? Derivative. Ooh, remember that? Well, you don't have to know this for this course. I'm just telling you there is this formula. But I'm just telling you, and you're not going to be computing these things, the derivatives, in any of the exams. Okay? So, and what's this? It's an integral. There's a relationship between a derivative and an integral. They're sort of, again, opposite sides of the coin. So if you're going from a hazard function to a survival function, you take this integral and you exponentiate it. If you're going from a survivor function to a hazard function, you differentiate something, you divide it by this, and then you get the hazard function. Okay. Now, key thing again is survival function and hazard function are opposite ends of the coin. If the hazard function is low, the survival function is typically going to be high. And if you know one, you can determine the other, as these formulas say. For example, here's an example. Here's an example of a certain hazard function. What kind of a hazard function is this? It's called a constant hazard function, right? At any time t, the hazard function is the same. Isn't that what that says? Now, the value for what the same is called lambda, but could have been 3. Could have been 1.3, but I've just got lambda in there instead of writing a number. But this says if you have a situation where a data set where the hazard function is constant, this would be how you'd graph it, because over time, the hazard doesn't change. The hazard function doesn't change. Well, if that's the case, you can do this little integral thing, and you could actually go through the integral and come up with the expression that says the formula for the survivor function is this. If the hazard function's constant, it's true if and only if the survivor function is this. This is called, you see, it's e to the minus lambda t. That's what this is called, the exponential survivor function. Why is it called the exponential survivor function? Because it's got an e in there. It's a survivor function where you're raising something to the e. Okay. Now, what does this function say? Well, if I graph it, certainly as when t is 0, what's the survivor curve? What's this function at time 0? 1. What happens as t gets larger? Gets smaller. So it's going to look like something like this. So if you've got a constant hazard function, then the survivor function is going to look like this. It's going to be called an exponential survivor curve. Now, if it's not constant, it could be other things. I'm not even sure if on the next, No, I don't have it there. There are other kinds of hazard functions you could have, and there are other kinds of survival curves, but one of them is the exponential. My point here is that if you know one, you can get the other. This helps you when you're doing an analysis, but let's go on to this one. Goals of a survival analysis. What do you want to do when you're doing a survival analysis? Well, in the example I started off with the remission time, what was the goal? The goal was to compare treatment with placebo. And you want to be able to say, is one doing better than the other? Okay? So that was the general goal. Okay? Now, it could be you're only looking, you don't have two groups, you only have one group. And you just want to see how those people in this one group does well. They're all getting a certain treatment. You want to see how well. So you might say, I want to see whether the survivor curve for this group looks like this or like this. If the curve looks like this versus like this, which is better? Which one would you rather have? If the people that are the outcome is bad, dying, you want to get the first one or the second one? How many say the first one? I heard some people say the first one, but the answer is the second one. Why is the answer the second one? Because the higher the probability, the longer people are surviving, right? This says these people are surviving, their probability for surviving is a lot higher throughout the whole time period compared to this one. So this is better, okay? So if you had this curve versus this group is doing better. I mean, but ideally what you want to do, if you're comparing two groups, you want to put them on the same graph so you can see what the survival curves look like. And that's what I've done here. So if you saw this, what would this say? I'm not saying, I don't have the data, I'm just, if you saw this picture, what would it say? Is treatment better than placebo? Well, not exactly. It is better early on, but is it better later? No, that's what it would say. So if you're comparing two groups, you want to say something over time. That's what a survivor curve does that a hazard ratio doesn't do. It shows you what happens over time. Hazard ratio is a summary over the whole time. Survivor curve says, how is the treatment of the placebo comparing at this time? Here, no difference. Here, the treatment does better earlier. Okay, so that's what that says. Now, so the goals is to either estimate a survival or hazard function or to compare survival functions, or more generally is what I've stated here, to assess the relationship of explanatory variables to survival time controlling for covariance. You see this statement? See this statement? What is this sort of another way of saying? Assess the relationship of explanatory, what do we mean by explanatory variables? Well, one could be an exposure variable. Another could be confounder. Another could be a product term. So when we talk about this, a general goal of survival time is the outcome survival. But you have some relate, you have a bunch of variables. One of them might be an exposure, and you might have variables you want to control for various reasons. And so that's your general question. So it's a similar question that we had for logistic regression. The only difference is we're dealing with survival data, not with binary outcomes. So and the last goal usually requires modeling using a Cox proportional hazards model, which is usually stated in terms of a hazard function. Okay, so more. Look at this. What's this? Well, what does it say? Basic data layout for the computer. Basic data layout for the computer. So what have I done on this slide? I said, well, it's just sort of like when I had those 6 people. Now I'm saying, suppose I have N people in my study. N people in my study. And this is the jth person. Well, the data layout, it's going to have a column for the survival time. It's going to have a column for the failure status, 0 or 1, whether they failed or were censored. And then it's going to have a bunch of columns for any of the explanatory variables we're dealing with, one of which could be exposure, another which could be age, another could be race, another could be, other variables could be product terms. So that's what the data layout looks like. You have a line of data for each person in your data set that describes what happened to them, whether they survived or their survival time, whether they survived or were censored, whether they were censored or their survival time, whether they censored or failed, I'm sorry, and what these other variables are. So that's one key thing. That's what the data layout looks like, okay? Now, there's one other data layout that's really important here. So if you're leaving, you're missing something, but it's recorded, you know, so anyhow, okay. So what is this data layout? This is a little trickier, okay, but this is an important one, okay? Now, you see I say ordered failure times? Ordered failure times. What's that mean? Ordered failure times. Well, what do you think T of 1 means? T of 1 with the parentheses. What's that? Ordered failure time. It's the earliest time that somebody failed. The earliest time that somebody failed. Okay? And T sub 2 is the second earliest time that somebody failed. The next earliest time. And T sub K is the latest time that somebody failed. So if I actually go to this thing, it's on the next slide. If I'm just looking at group 1, what's the earliest time that somebody in group 1 failed? 6. What's the earliest time that somebody in group 2 failed? Now, what's the next earliest time for group 2? What's the next earliest time for group 1? So it's different for different groups, right? Okay. Now, turns out when you set up this table, you also have time 0 where nobody failed, but you put that in there for a reason that I'll explain to you in a minute. Okay. Now, what you do is, this is the data layout for how survival analysis works. Okay. And what you're doing here is, in this column, it's the number of failures between one time and the next time. So, if we're looking at this study, this data set, we're just looking at, say, group 1, okay, how many people failed from the start of the study until the first time that somebody failed? How many people failed? Well, actually, what does this say? How many? This doesn't say that. How many people failed at the start of the study? None. Okay. How many people failed between the start of the study and the first time that somebody failed? What's n sub 1? What is it? 3, right? There were 3 people that failed between the start of the study and the first time that somebody failed. So that's T sub 1 is 6, okay? Okay? 6 people failed at time 6, okay? Now what's this? The number censored in this same time interval. Then you figure that out for group 1. The number censored between the first time that somebody failed and the second ordered failure time that somebody failed. Can you figure that out? What's the second time that the second ordered failure time? 7. So how many were censored from the first time that somebody was failed until the second time that somebody was failed? 1. Which one was it? 6 plus, right? So it's 1, right? I don't know if I'm pulling the wool over you, but it's 1. And that's how it goes. Now, it turns out that, so there's this column for the number of censored, okay? If you add up all the numbers in this column, what do you get? What do you get? Total number of people that failed. This is the number of people that failed at time 0, nobody. The number of people who failed at this time, number of people who failed at this time, add them all up, you get everybody who failed. If you add this up, what do you get? You get the number of people who were censored. That's what you get. Total number of people who were censored. So then there's this thing called the risk set. It's very important to know about. So I'm doing this now. Okay. The risk set The risk set is the subjects that are at, the collection of subjects that are at risk at any given time in this list. Now, at time 0, when nobody failed, who's at risk for failing? Everybody. Okay? Everybody's in the risk set at time 0. Okay. Okay, what about the next thing? Who's in the risk set at time 6? Well, this is a little tricky, because what you're asking is, who was at risk just prior to time 6? Who's at risk for failing just prior to time 6 when 3 people failed? How many were at risk? Everybody. Everybody was at risk just prior to the time that 3 people failed. How many are at risk here? I don't know if you can figure that out. Not how many. Who's at risk at time 7? Who's at risk at time 7? What are the people in the risk set at time 7? Well, are these 3 people in the risk set at time 7? No, because they already failed. Is this person in the risk set at time 7? No, because they already were censored. So the risk set at time 7 doesn't include these 4 people. That's how you do it. That's tricky. So you can go through this, and here it is. I mean, this is what it is for group 1. You notice how I had 6, 3, 1? That's what I showed you already. 3 people failed at time 6. 1 was censored between. Now, look at this. At time 7, 1 person was censored, and 1 person failed, and 1 person was censored between time 7 and time 10. Who's that? Who's that? Who was censored between time 7 and time 10? The 9 plus. Okay? So that's what you're doing here. Now, the thing is that when you do this, when you set things up this way, you're allowing yourself to figure out how to get a survival curve, how to plot a survival curve, by considering the fact that some people are in the data set up to a certain point, and then they drop out. And once they drop out, you don't count them anymore for later time points. And we'll see this next time. Okay, now, before I quit, I still got 5 minutes. Now, here's another situation. What have I done here on this slide? Got 5 more minutes. What have I done on this slide? I've added something to the so-called the data. I've added another variable. What variable have I added? Log white blood cell count. Why did I add white blood cell count or log white blood cell count? Because log white blood cell count is a known risk factor for leukemia outcome. So if the white blood cell is high, that's bad, right? Or the log white blood cell count. Now, in this case, people have decided log white blood cell is a better measure of that. So the purpose of this data set, I've expanded the data, I've extended the example. We still want to compare groups 1 and 2. But what we want to do is we want to be able to compare these groups, but we want to control for the fact that there's a variable that's maybe a confounder, or maybe it's even an effect modifier, white blood cell count, or the log of white blood cell count. How do we control for variables? How do we control for variables? Well, one way we do it is we stratify. We could basically look at high log white blood cell count and low log white blood cell count and compare the 2 groups for different strata. Or we can use a model where log white blood cell count is a variable in the model. Okay, now here's what I'm going to do. I'm going to go from this thing to the following thing. Now, by the way, this is all the data for group 1 and group 2 together. So if you wanted to evaluate this result, the question, and you wanted to control for log white blood cell, and you had 2 groups, you don't have 21. You have 21 in one group and 21, but you have 42 people in your study. So the data layout has 42 lines of data. It doesn't have 21 lines of data. It has 42 because you've got 21 in one group and 21 in the other group. Okay? So suppose you do the following. Look at this. This is the last thing I'm going to show you. Suppose I do this. This is a computer example of a Cox proportional hazards model. I haven't shown you what the model is, but I've got model 1, model 2, and I even have a model 3. Look at model 2. What variables are in model 2? Can you tell? Can you tell? I know it's just a few minutes left, but can you tell? Can you look at this? You've looked at logistic regression output. What are the variables in model 2? Treatment and log white blood cell count. What are the variables in model 1? Just treatment. What are the values in model 3? You've added a product term. Okay. Now, suppose I didn't know anything about what the Cox model looked like, but I'm looking at model 3. What would I want to do with this model, based on what we've learned last up to the midterm? Modeling strategy. What would we want to do? What would we want to assess here? Interaction. How would we do that? Well, either do a wall test or a likelihood ratio test. If we're doing a wall test, can you tell me what the answer is? What's the answer? What's the answer? Wall test. Here's the 0.51. That's the p-value, right? Significant? No. So what does that suggest? You don't need this term. Okay. What if I wanted to do a likelihood ratio test and I had model 3 and I had model 2? What would I do? You notice you see minus 2 log L? See that? And you see minus 2 log L here? With covariates, 144.131. With covariates, 144.559. I would subtract one of these log minus two log L, model 2, and the other one from model 3. I'd subtract one from the other. And I'd get a chi-square statistic with how many degrees of freedom? 1, and would it be significant? Wouldn't be significant. It would be almost the same as the wall test. So what does that say? There's no interaction. Have I shown you the model? No. Have I shown you the output? Does the output look familiar? Well, it's familiar, but it's not output from logistic regression. It's output from survival analysis, from Cox regression. But the output looks almost exactly the same, right? So that's why this isn't that hard. Now, let me ask you the last question before we quit. For model 2, okay, what's the estimate of the hazard ratio for the effect of the treatment variable for model 2? Now, notice model 2 is a no interaction model, correct? We dropped the interaction term. It's a no interaction model. So it has a coefficient estimate for log y plus O and a coefficient estimate for treatment variable. And treatment, it's a 0-1 variable. You're either exposed or unexposed. What did we do for logistic regression to get the odds ratio? What did we do? E to the beta, right? E to the beta. What do we do if it's survival analysis? E to the beta. It's the same formula. So e to the beta turns out, e to the 1.294 turns out to be 3.648. That's what it turns out to be. Now, even though this says risk ratio, the most current version will have hazard ratio over here. It'll be e to the beta. So what you see is, so what is 3.648? What is that? What's that? That's the hazard ratio for this remission time data when you're controlling for log white blood cell count and you're comparing the treated group with the placebo group. Is that a high hazard ratio? I mean, that's almost 4. Is it significant? Is it significant? Wall test. Is the wall test significant? 0.0022. So I've done a modeling thing. I haven't shown you what the Cox model looks like, but it's the same stuff. That's why I wanted to keep you here at least until 3 minutes after 20 after. Okay? So we'll talk about this again, but it's the same stuff. Looks exactly the same. Aaron. Hiya, let me do something so I don't have you on the recording.